let's switch to our keynote session. I'm really looking forward to this. Now, today's keynote is going to be by Petrik Clarberg. He's a principal research scientist at NVIDIA Research, where he joined the real-time rendering research team in 2016. Most recently, he has focused on systems and algorithmic research for real-time path tracing. Prior to NVIDIA, he was a real-time rendering researcher in the industry for many years and co-founded a startup. Petrik's passion for graphics started with the 1990s Denoising. He received his PhD in computer science and engineering from Lund University in Sweden. So let's hear from Petrik.
Hello everyone. I'm very happy to be here today, virtually at least. My name is Petrik Clarberg. I'm from the real-time rendering research team at NVIDIA. So over the last few years, we've explored real-time path tracing. The goal has been to build a full real-time path tracing pipeline, push it to its limits to see where it breaks. So I'll talk about the findings from this work today. A large number of people have helped with this effort. So I especially want to call out my closest collaborators who are mentioned on the slide here. So I'll divide this into two parts. Part one, I'll show a bunch of visual results, talk a little bit about the technical side of the path tracer. For the ones who saw my GDC talk earlier this year, there will be some amount of overlap, so please bear with me. But I've also added quite a lot of new content. Then for the second part, I will focus on open problems, the type of things we're currently thinking about. What are the next steps for real-time path tracing? So stay tuned for that. Ladies and gentlemen, this is real-time path tracing today. This is rendered on a single RTX 3090 GPU, 1080p resolution, as are all the results I'll be showing today. So here we're following paths of up to 30 bounces in length without any hacks or approximations. The path tracer itself is an unbiased path tracer, and then we'll take the output and denoise that to produce the image. I like this tiger shot, even though we've shown it before, both because it looks very real, and second because the stats for the scene are just impressive. So the tiger is a skinned character. It has a mesh with the bones and animations inside, and then there's a fur that is explicitly modeled with hair strands. In total of 3.5 million hair segments. It's walking through this very dense jungle, which consists of 3 billion instanced triangles. And especially here, note the FPS counter in the top left corner. So it's running this particular shot 33 FPS. It's stable at above 30 FPS throughout the animation. So what led us to this point? It's really the dream, which I think I share with many of you in the audience, is the dream of being able to take any 3D content and render it photorealistically in real time. And we define real time here as 30 milliseconds or less per frame. So how does one render something photorealistically? I'll keep it short. So the mathematics are described by the rendering equation, which was introduced almost 40 years ago, and even before that in other fields like physics. So path tracing solves the rendering equation by stochastically sampling the incident lighting. That is done by tracing paths that bounce around in the scene until they randomly hit the light source. In order to increase the chance of actually hitting a light source, a technique called next event estimation is often applied, where we at each bounce explicitly sample the lights by randomly picking a light and then tracing a shadow ray towards it to evaluate the visibility of it. So path tracing is an elegant solution to the render equation because it takes all types of light transport into account in the same framework. And it has completely taken over visual effects and film rendering over the last 10-15 years. However, it is computationally intensive because you have to, first of all, you have to trace a lot of rays. At each point along the rays, along the path, you have to do the shading, you have to do light sampling, many other operations. And then second problem is that since these paths are random, There's a lot of shader divergence and very random access to the memory. So in addition to that, why is real-time path tracing particularly hard compared to offline rendering? So there's several reasons for that. One is just the sheer difference in the computational time that is available. So for film rendering, it's common to have a rendering time of 24 compute hours or more per frame, whereas in real time, we have to stay under this 30 millisecond limit. And out of those 30 milliseconds, some of that is other things like denoising and everything else that the application has to do. Another more subtle difference is that in a film or a visual effects rendering, the shots and the lighting are carefully directed. Whereas in real time, many times the camera is a free camera controlled by the user. You can walk around anywhere in the scene, and the light transfer just needs to work wherever you look. And then third, for professional film rendering, the content and the art is often trained what to do and what not to do to avoid breaking the render. Whereas in real-time graphics, many times the content might have some issues. It might even be user-created content. The contents may be made for a rasterization engine that has very different requirements than a path tracer. So for all of these reasons, we say that real-time path tracing is at least a 3 million times as hard problem as offline rendering. So let's look at some results now. So to make real-time path tracing more useful for graphics research, we've recently added a PBRT scene importer that loads the scenes that are used for Matt Farr's book, Physical-Based Rendering. Those scenes are typically used for offline rendering research, but as we'll see, these are now available for real-time path tracing use for real-time graphics research. So in the background here, I'm showing the landscape scene, which is the identical scene as was used on the book cover for the 3rd edition of the book. You can see that the renders at 38 frames per second. This is with 10 bounces of path tracing. And the stats here are 4.3 billion instance triangles. Another metric that I want to point out is that the scene has over 400,000 instances. So I will now, here you can see the scene without the book covering it, and I will now show some more screenshots of it. So here is looking over the fence. This is at 35 FPS. And then there's a pond in part of the scene, so this is showing the reflections in the water surface there. You can see the very dense foliage that is reflected off the water here. And then for this view, this is at 43 FPS. So all of these are directly just screenshots from the real-time path tracer. So again, I want to point out that this is no longer seen only exclusively for offline rendering use. You can now actually path trace this in real time for your research. So path tracing is often associated with rendering glass and transparent materials. It's hard to fake those kind of materials without actually following the full light paths correctly. So to show an example of this, I've here loaded the transparent machines scene. This is actually made by the same artist at the 0 day scene that I'll show in a moment. This gives a good idea of what's possible in real time today for glass and other transparent objects. So you can see we're tracing this with 30 bounces of path tracing. The object itself has 3.6 million triangles and about 851 mesh instances. So as you can see, there are still some black spots in it. Those are indications that some paths still at these number of bounces get stuck with total internal reflection, and that you would need even more bounces to remove those. We've tried with 100 bounces, then it runs slightly lower than 30 FPS, but still fairly useful. So one of the things I mentioned in my GDC talk was adding support for more complex materials to the research path tracer. We've now done that over the last couple of months. We've added support for all the real PBRT materials, including coded diffuse, coded conductors, and also support for the measured MERL and the anisotropic RGL materials from the EPFL database. So this scene, the sports car, uses almost entirely these measured anisotropic RGL materials. So it's an example of showing rendering with these other material shaders. Here we also using the same settings here. These are the defaults for the path trace of 10 bounces, has 7.2 million instanced triangles. So this is an outdoor scene, of course, so it's a fairly simple light transport, but there are some effects like the rear lights you saw, the windscreen, and some other parts where actually many bounces are required. So here is another very common scene from rendering research. This is the PBRT country kitchen scene that we path trace also in real time. This has been used in numerous rendering papers. You probably recognize it. This runs at stable 60 frames per second. And then similarly, the PBRT bathroom scene. This also again renders at about 60 FPS. The main challenge in this scene has been the denoising of the glass light bulbs that you see hanging above the mirror. So keep an eye on those when I play the clip. And that case is particularly challenging because it's denoising something that's only seen through reflection. So as you noticed, all of these PBRT scenes are static, but we also wanted to show an example of dynamic scenes because the path trace has no pre-computation, so you can really handle anything that is dynamic and both moving light sources and moving geometry. So for that purpose, we have this 0-day scene done by digital artist Mike Winkelmann. We've shown this several times in different demos over the last years, and the reason is that it's a really good stress test for the denoiser, and every time we show it, we have some improvements. So as you can see when I play it, it features very glossy materials, makes it hard to denoise. It's also very quickly moving lights and moving geometry. Performance here is around 60 FPS, 3 bounces, and 6 million instance triangles, and then the lighting comes from 10,000 emissive triangles. And when we saw this when we saw that we were able to render this in real time, we really thought that we need to push this much higher and see where the limits are. So therefore, we got this beautiful scene of Turbo Squid, which is really made for offline rendering. It's incredibly detailed when you zoom in. Look at the details, like the chandelier and the chairs and all parts of it. Here there are 25 times as much geometry as in 0-day and 50 times as many lights. So the lighting comes from 500,000 emissive triangles, and then on top of that we have added 30 dynamic spotlights to make it even more interesting and also dynamically changing. So both 0-day and this scene are indoor scenes with we used 3 bounces of path tracing for them. Performance for this scene is about 30 frames per second. 0-day was 60 frames per second. So that shows how well path tracing scales logarithmically with increasing complexity. There's more than an order of magnitude more geometry and more lights, but only half the performance. So finally, I also must show the tiger in action. This is a live capture from a path tracer. It runs stable at 30 frames per second. As you can see, the tiger's walking here along the waterfront. The jungle is not seen much in this shot, but it's actually 3 billion instance triangles. The main complexity is the light transport in the fur for these images. And the lighting comes from an environment map and then a separate distant sunlight. That light is filtered through the canopy, and the leaves have a diffused transmissive material. So this kind of illumination is just very difficult to approximate without path tracing. Here is to give you a sense of the scale of the jungle. I've circled the location of the tiger with the red mark. So when I play now, you can look closely there. You can see that it's walking on this little island, and the camera will be moving around to show you a bit of the scale and what it looks like more up close for the trees. And then finally, we also wanted to test animated foliage. That's a particularly tricky case because it requires updating the BBH, the acceleration structure, every frame for a large number of triangles. So to do that, we've added a wind animation. So the leaves here are swaying in the wind a little bit. And also note that we don't use any alpha testing and no LOD for this scene. So it's really just path tracing against the geometry at the finest scale. So every single leaf is modeled with triangles here. And in a real application, I should say, you probably want to use both LOD and alpha testing to reduce the complexity. But nevertheless, performance is very good actually. It's between 45 and 50, 60 FPS. As you can see, when we drag the slider here, the time of day changes. So both the environment map and the lighting changes, and the leaf animation changes. So let's talk about what are the most important performance optimizations we've done. A lot of this effort has been about understanding path tracing performance on the GPU and avoiding bottlenecks. So maybe the most important is optimizing for cache efficiency. So the GPU has this memory hierarchy with a large chunk of DRAM and then smaller caches. We really need to make the best use of these caches. And since path tracing is essentially a random access algorithm, it's really important to both compact your data as much as possible so that you can fit more in each cache line. Think about cache line alignment of your data structs, minimize the number of indirections when you do access memory. Really, everything you can do to minimize the number of cache lines that are touched when you do access memory from within the path tracer. Then another important aspect is material complexity and number of shaders executed. I mentioned earlier that one of the problems is shader divergence. If you have thousands of shaders, then it's very difficult to schedule that in a good way. So what we do is we kind of taken a drastic approach for the research path tracer to bake down the original MDL material shaders into a smaller set of PBR material models. And then we're taking a bottom-up approach to gradually add back more material shaders. So for example, we've added now back all the PBRT materials, we added measure materials, but we do this carefully to see how much complexity we can bring back while still maintaining the real-time rate. Third, we've done a lot of scheduling experiments over the years. I can't go too much into detail on that, but one of the main conclusions has been that when you have any kind of wavefront architecture where you trace one bounce of path tracing, write out all the hit points to memory, and then maybe sort and then trace the next bounce, any kind of wavefront architecture like that is always going to be bottlenecked on the memory I/O. So that's why we say that it's really important to keep your work on chip as much as possible. And the recommendation is actually to leave the scheduling choices to the driver, because the driver has more low-level knowledge. It can decide when to run which shader to be able to keep the data on chip better. And then fourth, the important aspect is also optimizing your assets and in particular your BBH acceleration structures for ray tracing and path tracing performance. So the main challenge here is mapping the often deep scene hierarchy onto the one-level instancing hierarchy that the ray tracing APIs provide. And what to optimize for there is to minimize the spatial overlap between the bottom-level acceleration structures just to increase traversal performance. So now we've taken all these optimizations and implemented them in a full real-time path tracing pipeline. This pipeline consists of three main parts. There's a front end and then a light transport phase where the majority of frame time is consumed, and then a post-processing pipeline which denoises and produces the final image. For the front end, this is fairly similar to what current raster engines do, at least the engines that support ray tracing. So it's handling all the scene updates, it's updating the BBH acceleration structures if they're animated or skinned content. And then we also include a VBuffer pass here to compute what is visible from each pixel. And the reason to do that is that this information is needed both by the path tracer to launch the paths from, and also by the post-processing pipeline for the denoising and post passes. So it makes sense to amortize that cost. Second, as I mentioned, the light transport phase is the most complex. Here we use the GeForce SDK called RTX DI, which is based on Register. It's a productization register. We use that for the direct lighting. It handles diffuse and glossy reflections. And then the path tracer simulates all other types of light transport. We usually run that at between 3 and 30 bounces. So that includes ideal specular reflections, a transmission, all types of transmission, all the indirect lighting, and so on. The path tracer also outputs guide buffers, which the denoiser then consumes to be able to produce the image. And we also in the code have an option to enable a probe-based irradiance cache that is provided by the RTX GI SDK. We do not use that for any of the results that we show today, but it's an option to enable that to get even better performance by then reducing the path length and instead terminating them into this irradiance cache. So, and then finally there's the post-processing pipeline, which is really critical for producing the image. We built this on top of the NVIDIA's real-time denoiser library NRD. So NRD provides a set of spatial temporal denoising kernels. We combined those in a way, I'll show an example of that a bit later. We also run DLSS, the deep learning supersampling. We run that at 100% and no super res, just to provide anti-aliasing a little bit, remove some residual noise that is left by the denoiser. And then there's some post passes, very traditional tone mapping and maybe depth of field and bloom and so on, if those are desired. So this completes the pipeline. You can, we have source code for this that is open source. So you can go look at all the parts of this and how it works. So finally, I'm sure you wonder now, how is the time spent between these three phases, between the front end, the light transport phase, and the post-processing. So I've measured that on 3 different scenes. First, the tiger scene, which is the most complex of the ones we showed today. In that case, the path tracing itself is about 50 or so % of the frame time. The rest is the front end work, where there's quite a bit of animation and updating of the BVHs, and then the denoising and post pipeline there that takes the rest. Landscape scene behaves similarly. It's a similar complexity in the number of triangles and actually the look of the scene itself. So the light transport there is on par with the tiger scene, even slightly more. But the front end work is less because it's not animated. And then there's the transparent machines with 30 bounces of path tracing, where the light transport phase is about 13 milliseconds. And then finally the car scene, where the majority of cost is actually valued in these measured RGL materials. The code for those are fairly complicated. So I want to say a few words about the implementation of the path tracer. So the implementation was a challenge on its own. And one fundamental observation is that path tracing is a unified rendering algorithm, and therefore all the rendering code that is needed for the frame needs to be available at the same time. When you trace array, you can hit anything in the scene. You need to be able to shade at that point, you need to be able to do light sampling, update the dielectric stack, do all the logic for the path tracer, and so on. So you really need all the shader code in one place. And we've implemented this as a single DirectX ray tracing program. This program have then different entry points for the ray generation shader, for the different hit shaders, any hit shaders if there's alpha testing, and the large amount of shared shader code for all the BSDFs, the materials, light samplers, everything else that's needed during the frame. And as I said, the complexity of this gets very large because it's everything that is needed for the full frame. So even for the research path tracer, this is already up to tens of thousands of lines of code, shader code. And we quickly realized that current shading languages like GLSL and HLSL, they're not at all built for this kind of complexity. So the question is really, how do you write modular and extensible shader code to support, all these different sampling strategies, all the different materials, depending on what the scene needs, and able to dynamically add or remove those without creating a mess, unmaintainable mess of the shader code. So to address this, we build on the Slang shading language. So Slang is foundational technology for NVIDIA Omniverse and also for all of our graphics research. The goal of Slang is to support exactly this use case, being able to write large production shader code bases in a modular and extensible way. And the strategy often taken is to adopt carefully proven mechanisms from other languages like Rust and Swift, and then implement them in Slang in a GPU-centric way, so that performance still is as good as it can be. And many of these features have actually been co-developed with the path tracing research. So we developed the language jointly with the path tracer. Slang is open source, and it also compiles to a large number of APIs, including Vulkan, DX11, DX12, CUDA. So, and the important thing is that it's backwards compatible with HLSL almost entirely. So if you have existing shader code, it's really easy to switch to Slang and then benefit from all these modularity features it provides. So I won't have time to go into too much of what it can do, but I'll show one example of something that is very useful. So Slang has this concept of interfaces. An interface is kind of like a base class in C++ that tells you which operations a type can implement, but not the actual implementation of those. And then you write your implementation, in this case, a random number generator, that then implements these interface operations. And the power of this is that now you can have many different implementations of the same interface, and you can write generic functions that then operate on the interface type without knowing exactly what type you pass into it. So that the types then can be either they can be either statically created or even dynamically created in Slang, but your rendering code can be written generically to handle any kind of thing. So this is super useful. We use this for all the essentially everything in the path trace. We use it for all the BSDFs, all the materials, the light samplers, and everything else. So here I wanted to show you some pointers to source code. So as I mentioned, the Falcor real-time path tracing research renderer is fully open source. It shows you how to integrate all of these NVIDIA SDKs that I've mentioned: RTX DI, RTX GI, DLSS, NRD for denoising, and MDL for the material description language. It shows you how to integrate this in a real-time path tracer. And since we are limited on time today, I'm going to leave it there. But you can go see my GDC talk for more details on the technical side of the implementation of this path tracer. So the link here points you to that talk. Similarly for the Slang shader compiler, of course, you're free to use that independently of the path tracer. But Falcor is using it throughout, so all the shaders you'll see are written in Slang, and same here, we have a longer technical talk that you can go watch if you want more details on what Slang can provide and how it's built and what APIs it can target. So that concludes the first part of this talk. Now we can stretch our legs a bit for 1 second and think about what we've just seen. Real-time path tracing of really quite large and complex scenes, including the well-known PBRT scenes, which are now available for real-time graphics research using path tracing. I would say that these results have fundamentally changed the way we think about real-time graphics research. There are no more shadow maps, no ambient occlusion passes. It's really unified onto improving the light transport, improving the denoising, improving the content. So end of break. For the second half, I want to focus on what is next, the top 3 areas to improve on, and with this dream in mind of being able to photorealistic render any type of 3D content. So, as I mentioned earlier, real-time path tracing often do not have as much control over the content as an offline production. So an important open problem is more robust and better sampling methods that can handle even in some cases poor content. So here's a simple example I'll be used to illustrate one of the many common problems we see. Both images here are path traced with identical settings. It runs at about 150 frames per second because it's a very simple scene. But the right one doesn't look quite right. If you look closely in the corners, for example, there's blotchiness, it has weaker color bleeding, and generally it's a bit darker than the one on the left. But it's supposed to be an unbiased rendering, so what is really going on? And this is a common question that is not always easy to answer. So when loading arbitrary content into the path tracer, sometimes it works very well, sometimes it doesn't, and it's important to be able to find out why. In this case, where if I turn off the denoiser, you can see that the samples on the right are almost entirely all black. So the denoiser has very little data to work with and hence produces these bad results. But why is the sampling so bad? This requires some detective work to figure out. In this case, I know because I created it myself, but the reason is that we placed some bright lights outside the scene. They're always occluded, but they fool in the light sampling. And you would actually be surprised to find out how common this is in real scenes. There are many cases where there's super bright lights and they're just always occluded for no particular reason. Is this a content problem or a sampling problem? Well, I guess that depends on who you ask. Do you ask the artists? Then it's maybe more of a rendering problem. If you ask the rendering engineers, then they'll probably say, can you please go fix the content? But independent of that, we need to handle it. So I'm going to show some other examples. That was a case of lights outside that are always occluded or almost always occluded. Another common problem is that there can be lights that are hidden inside of walls or partially inside of walls. Sometimes geometry is not properly closed, so some paths can escape into the interior of walls and so on. That can cause both issues with the volumetric stack and also performance issues. Sometimes emissive textures are very poorly used in that there can be a 4K emissive texture with only a few pixels actually lit up. Again, causing problems unless you're very careful to pre-integrate your emissive texture against the geometry, or otherwise handling where to sample on them. So in general, some of these issues are just caused by real-time content being authored for real-time engines, where these things maybe don't matter for the performance or the visual quality. Practically speaking, though, we realize that raster and path tracing will coexist for quite a while, so we cannot expect content to suddenly get a lot better. It's also very expensive to make fixes to the content. It requires talking to the artist, getting their time to actually fix these problems, that they have to understand what is causing it, and so on. So for that reason, I would say that more robust sampling methods that can handle even bad content are needed. And then second, I also think we need better tools to understand where and what is causing a particular rendering issue. So for association work, there are by now very well developed tools for analyzing performance problems or looking at where issues are coming from. We need similar suite of tools for real-time path tracing. So I will show an example how better sampling can help address this problem, even without changing the content. So here I've taken this bad version of the kernel box with the extra lights. On the left we show the original path trace output. In the middle, I show what happens if I enable RTX DI for the direct illumination sampling. So that takes care of sampling the direct illumination very well, even though many of the lights are occluded. And then on the right, we also enabled Restore GI, which is a solution for at least diffuse-ish indirect illumination using the Restore mechanism. So in that case, that is sufficient to handle this problem, that it's enough for these algorithms to find a few useful samples and then they're able to reuse those. So what about more difficult light paths? So this year, researchers in our group, in collaboration with University of Utah, have extended full path tracing, extended Restore to full path tracing. So in this case, we show the classical Vechian Guba scene, where lighting comes in through a small crack in this door, and then has to bounce several times through the scene in order before reaching the camera. So this is of course a notoriously difficult case to sample. It's often used for light transport papers to illustrate improvements in the sampling. So here I'm showing the path traced original output. This is with just traditional BSDF sampling, next event estimation, which in this case doesn't really help because the lights are not visible. Enabling Restore GI, which handles diffuse and glossy illumination on the secondary bounces. So note that the teapot in the front, which is very highly glossy, and also the teapot in the back, which is transparent, those are just not handled by this algorithm and turn out to be black because of lack of sampling. And then Restore PT, this year's extension, is actually able to find useful samples even on these type of materials. And here's the reference for solution for comparison. So the previous image was one sample per pixel, and this is using this is converged. So I'll show it in action. So as you can see, this is running at about 40 milliseconds per frame. Restore PT is not yet fully integrated into our real-time path tracer. The method is fairly involved and was developed in a separate framework, but that's one of the things we're working on to merge these two. So Restore is extremely successful at improving sampling quality. Once you've found an initial set of samples that are useful, then Restore can improve the quality of those samples. But you still need to find these initial samples, and sometimes that's very hard. Next event estimation is actually very fragile. Whenever your light source is inside glass, for example, or in water or outside water, you're in the water, whenever there's an interface between you and the light source, then traditional next event estimation just fails, and your shadow rays will always be occluded and just wasted effort. So one of the things to improve on is better next event estimation. One solution might be to implement specular next event estimation or specular manifold sampling and port those algorithms to real time. Could be very useful, I think, even though it's fairly complicated. Another open problem is sampling longer light paths through things like very long blonde hair, snow and ice, other media that requires many bounces, and then connecting to light source when you exit the media. So this photo actually combines it all. This is caustics lighting up long fur that is light color underwater here. So when we can render this in real time, we've made quite some progress. So as I mentioned, similar problem happens with snow and ice, and that's the reason we don't yet have any winter scenes in the real-time path trace results. It just doesn't work yet. So those were some challenging problems with sampling. Let's talk about denoising as well, because sampling and denoising are intrinsically tied together. Real-time path tracing would not be possible without both, and there's definitely room for improvement. So a path tracing denoiser uses the NRD kernels, and I'm going to keep this short, but what we're doing is essentially take the noisy path trace signal, decompose it into different frequencies, so diffuse reflection, specular reflection, transmission components, and so on. Then denoise those separately, and then combine the result again to produce the image. These kernels are essentially very fancy edge-stopping blur kernels that reduce samples both spatially and temporally. They're guided by a large number of guide buffers that the path tracer produces. So the expectation is that most of these guide buffers are noise-free or low noise, so that the kernels can make appropriate decisions about the size of the blur kernels, how to weigh the different samples over the kernels. So what happens if this guide data is not clean, if it's noisy instead? So and that can be a challenge when there is, when the guide data just becomes noisy and the signal itself is actually quite low frequency and should be able to be denoised. So some examples where this happens is that when you have very dense geometry, so that's actually the case in the landscape scene, that you have this extremely high depth complexity and very, very fine subpixel geometry, even though the color in the end is mostly greenish yellow and should be fairly okay to denoise and blur at least some components of that. Similar with the hair rendering, there's also a case of very fine geometry. Volumes is slightly different in that a volume doesn't have a well-defined surface. It's actually defined by the random walk through it. So when you do take attributes to use for the guide data there, those are noisy by definition, and it causes problems with the denoiser. Another case that I don't have an image for is particle effects, which can also be tricky. So I will now show you the example of the landscape scene animated. So when I play this, you can see that there's a little bit of flickering left in some parts, especially in the tall grass, where there's just a lot of very thin subpixel geometry. Overall, we're still very happy with this result, to be able to even path trace it in real time at all, but I think there's room to tweak the denoiser a bit more. So we're coming up to the foliage here in the back, and then the camera's going to turn around and look over the pond. So you can especially see the this slight flickering on the grass field here. Similar case, this is the PBRT hair scene with 6.8 million curve segments. We also used 10 bounces for this. I apologize for the rough camera motion here, but it's just really to prove I'll show you an example of where denoising is currently failing. So another interesting problem is Codesign of the sampling and denoising algorithms. We already do this to some extent because we make sure to output specific guide data that the denoiser needs, and those two have been developed together. But it's often the case that the denoiser actually knows where the signal is sufficient and where it isn't. So we'd like to feed this information back from the denoiser to the path tracer to control the sampling. And path tracing, unlike rasterization, actually allows very fine-grained control over where and when to sample. So you can decide things like samples per pixel, the path length. You can even do things like dynamic path regularization to make materials on secondary bounces more diffuse dynamically to make the light transport easier. So there's just a lot of knobs that you could control to control the sampling quality, both spatially and along the paths. And the goal is really end-to-end to optimize for the best image quality. And one example we did a couple of years ago is this neural denoiser that is trained end-to-end, including the path tracing, that is then an adaptive path tracer, and then with a learning-based denoising pass. So that's an example of this kind of co-design. And once we have this kind of control, that the path tracer can be controlled at a very fine grain of where and when to sample, then the question arises, is it time for fully frameless rendering? So by frameless rendering, I mean that the denoiser and the image generation pipeline runs entirely decoupled from the sample generation. So you can imagine running the denoiser at a fixed frame rate of 60 FPS or even 120 FPS. And then for every time it needs to generate an image, it takes the currently available samples and generate the image. And then in that scenario, the path tracer run asynchronously to add, remove, update samples, as many as it can during its continuously while it's running. The main benefit of this kind of system would be that there's no risk of dropping a frame. You always get an image out. It's just the quality of that image maybe varies. But for real time, that's a good trade-off because you do care about fixed frame rate. And also, if you get a faster GPU, then you automatically get more samples and a better image. So it has a very nice scaling behavior. With fully frameless rendering, it would be very important to think carefully about where to place your samples. And the best way to do that is through a good, for example, a blue noise sample distribution. So we had this work last year that produces this kind of spatial temporally optimized blue noise pattern. So that's a reference for that if you're interested in frameless rendering. So now we're coming to the last of the open problems. So assume for a second that we have solved sampling and denoising, and that you can take any existing 3D content and path trace it in real time. Would we be done yet if we reach that point? And well, the answer is no, because I would say that there exists very little 3D content today that can truly produce lifelike photorealistic renderings. The world is just incredibly detailed, and this is not a problem. I'm very glad it is, but it's a fun challenge to go after. So Detailex exists at all scales. These are photographs taken by Benedict. So as you can see here, there's when you go close to this branch, there's amazing detail that you see everywhere. Artists today are very good at modeling large scale detail like trees and hills and roads, but the smaller you get, the richer the detail gets, and the more tedious and time consuming it gets to model it. And it's just the sheer diversity of detail that makes it incredibly hard to do this by hand. Every object looks different close up. So just for fun, to see where we're at, I took the PBRT landscape scene, which has 4.3 billion instance triangles. And there's no critique on the modeling here. It's an amazing scene in the distance. But when you do move close to the detail in it, you realize just how much is left out. So here I'm showing some leaves, comparing those to a photograph I took when I was out running the other day. You can see that it looks nothing like the real world. So conclusion is that 4.3 billion triangles is not even close to being able to produce photorealistic results when you get close. And in a real-time scenario where the user has free control over the camera, you can't guarantee that they won't go close to a tree and actually look at the leaves. And I can only speculate that we maybe need 1,000 times more geometric detail. Here's another example. Now it's a bit unfair because I didn't find the same type of tree, but you get the point. Left is the rendering of a tree in the landscape scene. The right is a close-up of the bark on one of these trees, of the trunk. So there's really sub-millimeter scale detail everywhere. But this is not just a problem of geometric detail. Material fidelity also needs orders of magnitude improvements compared to current real-time PBR material models. This is an area where we can get a lot of inspiration from film rendering, because they, in many cases, work with deeply layered material models, and we really want to bring that kind of complexity to real-time materials. So that's a bit about the challenges of getting detail. So now let's consider for a second how real-time path tracing can help content creation. So an immediate effect is that with live feedback, whenever you make a scene edit, and directly see the path trace result at 30 FPS or 60 FPS, then when you don't have to wait for the rendering anymore, then the artist iteration loop can go faster. I think that's a very practical and near-term result that can make our content creation smoother and artists happier, but it's not going to give us orders of magnitude more fidelity. It just doesn't scale that way. So the other ways to get really detailed information is to get it from the real world through photogrammetry or other ways of extracting information. The other thing, which I think we're going to see so much more work being done in is really advanced generative models for creating 3D content and creating materials, where in that case you have an AI artist creating it and then a human artist controlling it and adapting it to what you need for the particular application. So as an example of the former, photogrammetry, we've done work in our team to improve photogrammetry. So for that purpose, we built a differentiable rendering pipeline. And then with this, we can jointly optimize both the shape, so the mesh, the material properties, and the lighting. So we can get, just based on multi-view photographs, we get all of these three components out, and then we can insert the reconstructed objects in 3D scenes and edit them using traditional tools. So this is an example of just one of the test data sets. Another question that arises is, when you have this insane amount of detail that we need to represent, how is that actually going to be stored? Triangle meshes and texture maps are good at many things, but they just don't scale, even with extremely high compression, which, for example, Nanite has done an absolutely impressive job of enabling. Even with that, we're still far off, and also many things are not well represented as triangular surfaces. So I think that interesting direction is to use neural encodings, this kind of data. Through numerous examples, we've seen that neural techniques can very, very compactly be able to represent very complex data. So there's, for example, neural BRDFs. We can encode a large set of measured BRDFs with tiny neural networks, as in this paper on the right here. We've done work ourselves on nerve textures to make nerves more useful for content creation, to be able to actually texture an object with nerves. And there's work from this year about compression of neural fields, such as radiance fields, that can provide a level of detail compression of these to a very high rate. So I think this is, we're going to see so much more work in this particular field. Finally, I think no one can fail to be impressed by the advancements of the latest huge generative models, such as DALL-E 2 and ImageGen, and also StyleGAN. So all of these tools, they, however, currently produce kind of postcards. They produce 2D images of amazing things. You can tell it, I want an image of this, and you get some image that is, just extremely impressive. But imagine a future where these models are not trained to generate images, but actually trained on 3D meshes or material definitions. And you can tell it, I want a mesh that looks like this, and you get the 3D mesh out. Something like that would really revolutionize content creation. And I think it's just a matter of time. So with that, I leave you with those thoughts. That was a bit more speculative. So let's wrap up. So the first message today is that real-time path tracing is here for real-time rendering research. The PBRT scenes are no longer reserved for offline rendering research, but you can actually just go grab our source code, download the scenes, and help us solve these problems. Second message is that offline rendering and real-time rendering are now quite similar fields in that they share the same underlying algorithms like importance sampling, denoising, and so on. But there's also a bunch of different both challenges and opportunities. One is that, in real time, we absolutely need to make a frame every, at a fixed rate every frame. So there's room for optimizing the sampling, denoising jointly, things like frameless rendering. It's also the case that content is not always perfect. Sometimes it's even user created, and the path tracer just needs to work, whatever content you throw at it. And if there's problems, then it needs to degrade gracefully. So you still get some kind of image out, but maybe it's too blurry or otherwise, but it is still a useful image at the right rate. So that's an exciting challenge. And then finally, as I talked about, getting to this dream we had of photorealistic rendering of anything. The big challenge there is really to address this, getting the detail in, both geometric and material detail, orders of magnitude more detail. So sometimes when I present real-time path tracing, I get the question that now when we can path trace in real time, is rendering now solved? And I see it from the other side, that now when we've opened this box, we can look at these assets in real time with path tracing, we'd realize just how much is left to solve. So it's a very exciting time for real-time graphics research, and that there's so many interesting problems, so many new opportunities. So big thank you for listening. I also want to call out all my collaborators across NVIDIA and academia, and of course especially the real-time rendering research team, where many of my colleagues are working. On the right here, I've included a list of references to all the papers I've mentioned in this keynote. So feel free to go look up those if you need more information. And previously, I showed the links to the Falcor research path tracer and the Slang shader compiler. So now I'm happy to take a few questions. I hope we have time for that. And thank you again for listening.
Thank you, Petrik. That was a wonderful talk. I'm surprised how far real-time path tracing has come. We are now able to take for 5 minutes a few questions from Petrik. Let's start with the one on the question board, and then others, I think you can use the come to mic option to ask questions with audio, or use the post question button to ask them in text. So the question on the question board right now is, you mentioned better caching highly improves path tracing. And according to the unofficial specs of the RTX 40XX, the caches will be far bigger. Can you say something about that already?
I can say it's true that caching helps a lot for improving path tracing. I mean, when we started going to larger scenes like the Opera House scene, one of the effects we saw that's really one of the things that is super limited by memory bandwidth. So 80% or so was traversal bandwidth for that, at least until we started doing more advanced shading in it. So that's a case that is super limited by memory bandwidth. And of course, if you make the caches larger, then that's going to help tremendously on that kind of scene. But of course I can't comment on pre-release specs and so on, of course.
Okay, we have another question on the question board. Can you elaborate a little bit about the BVH updates for foliage in the Tiger example? It seems like the sheer detail would end up requiring more than 2 BVH levels, and if not, that would require inordinate CPU time.
Right, that's a very good question, and it's true that there's a hard decision to make of what to put in the 2 levels of the BVH. In the Tiger scene example, we put entire trees as bottom level exposition structures. So entire trees are then instanced. You can imagine different choice, and I think the PBRT landscape scene makes a very different choice in that the individual bottom level structures are much smaller, individual leaves or individual branches. So that's really an interesting optimization problem of what to put in the top level and bottom level, and both optimize for traversal performance and also optimize for the update cost. So for the Tiger scene itself, where we put entire trees and instances and update those, the update cost was on the range of 2 to 3 milliseconds per frame, which I think was reasonable in that kind of complexity. But of course, if you have, and to be fair, I mean, the trees are largely identical trees, but they're rotated differently. And the human observer is not very. I mean, it's really hard to see that they actually a lot of copies of the same tree. So that's one trick you can use.
Got it. I also have a couple of philosophical questions while we're waiting for maybe a couple more questions from the audience. You talked about neural representation sort of also intersecting with the path that you're on. I was trying to, lately we've been seeing a lot of work where NeRF-like representations have managed to produce highly photorealistic renderings of both captured and synthetic scenes. Do you think is there a path to converge with that kind of representation and rendering method?
Yeah, absolutely. I mean, I think one of the big challenges is getting this, as I talked about, orders of magnitude in more detail. And one way of doing that is to have kind of a base geometry as your triangle mesh or whatever position, and then a thin layer, a thin shell of detail on it. And that shell might very well be a NeRF-like representation that you then, when you hit it with the ray, that you then do the computation for it. So I think some kind of hybrid representation like that might very, very well be, one way to get to this kind of very, very detailed geometry we talked about. One challenge in NeRFs in general is that they're excellent at representing captured data and reproducing that in a very, very compact way. But we also need it to be artistically controllable and animatable and be able to interact with it in the engine. So I think that's an important open problem in some aspects of that. How to compose a scene out of NeRFs or NeRF patches in a very seamless manner and be able to animate it.
Okay. Are there any questions on the mic or on the question board? If not, I'll ask one more because this is super interesting. In your experience, what are some of were there any natural or organic changes in the artistic flow that you experienced that was specifically evolved from having a path trace or real-time path tracing application where artists chose to take or not take specified sort of more conventional behaviors because the rendering pipeline is so different?
That's another good question. I mean, we have some in-house artists that have helped us with the content here, and one feedback is that it's a relief to be able to model something and see it accurately rendered, even in real-time feedback, without having to worry about how does it differ in the, how large are the approximations than the rendered version. The approximations here, I mean, the image you get out is not, of course, truly unbiased because it's denoised, but the denoiser is fairly well understood, and we try to minimize the amount of extra blur it gives. So you get a very, very good representation of the true lighting, the true glass, and everything else you have in the scene. So that kind of feedback at least made it much easier for the artist to quickly get the right look. And that's also what we hear from other partners when we talk about them, that being able to have a reference rendering that is really quick is something super valuable in all kind of real-time applications, really. Got it.
All right, we're closing into 10:30, so let's thank Petrik again for a wonderful keynote. We will have a 5-minute break after this point, and then we will return for the diversity. Thank you again, Petrik.